Hi there, everybody. In this section, we're going to keep going in Chapter 3, and we're going to look at how we build confidence intervals using bootstrapping. So let's get started. Alrighty. So the idea here is we're going to develop a concept called bootstrapping. And what it does is it takes the sample, your original sample, whatever it is, and it creates many copies of the sample. And it uses those copies to generate something that approximates a sampling distribution. And you'll see how it works. And what I'm going to do in this video, I'm going to put all the stat key at the end of the video. So everything's like in line with the slides. So don't worry about where the graphs come from and stuff. I'll show you at the end. And then you can go back and sort of redo what I do by following along with the stat key. So the stat key's at the end. It's a separate step. And we, again, obviously we're doing a lot of stat key in Chapter 3. So there's even more in this one. And so the distributions of sample statistics considered so far in this chapter require us either to already know the value of the population parameter, right? We saw that with the NFL contracts problem, or to have the resources to take thousands of different samples. In most situations, neither of these is an option. In this section, we introduce a method for estimating the variability of a statistic that uses only the data in the original sample, called bootstrapping. So what we're going to do is we're going to put this whole section inside this one example. And the example that I chose is called sandwich ants. And the question is, if a peanut butter sandwich is left on the ground for 5 minutes, how many ants will climb onto it? So it doesn't sound much like heavy-duty statistics, but it doesn't have to be, right? So this was a real study done in 1994 by an Australian high school student at the time, Dominic Kelly. So he left a piece of sandwich on the ground, counted the number of ants, and he did this 8 times, and here's the results. And so the idea is we would like to use just this one sample, very small sample, right? It's only 8 pieces of sandwich, to learn about the variability of all sandwiches left on the ground, right? And that's what's going on up here. So when we ask a question like this, we're talking about if you could somehow have the population of all sandwiches left on the ground for 5 minutes, what's the average, right? What's the mean number of ants, or how much variability is there? And it turns out that we can estimate that really nicely using just this one sample. So the mean of this sample is x bar equals 34, and the standard deviation is 14.63. But these statistics alone don't give us much information about the population mean. So before we go any farther, just think back to what we did in section 3.1 with the NFL contracts. We took one sample and looked at the mean and said, well, how close is this mean to the population mean? When we're talking about NFL contracts, we know the population mean. That information is public, we can look it up. But here, nobody knows the average number of ants that would climb on a sandwich in 5 minutes. That is impossible to be known and never will be known. But we can still estimate it to a certain degree of accuracy, right? And that's where the confidence interval comes in. So to get a range of plausible values for the population mean number of ants on a peanut butter sandwich, it would help to see a sampling distribution for means of many samples of size 8, right? So you would think, why didn't Dominic just do this experiment with 8 sandwiches and then come back later or go to a different spot and do it again and do that over and over hundreds of times or thousands of times? Well, that's not practical, right? That's a lot of work just to learn about ants. It's a lot easier just to put 8 sandwiches on the ground and see what we can learn about these ants. And we don't have access to the population of peanut butter sandwiches with ants on them. We only have the data for a single sample. So we can't go take lots of samples, and we don't know anything about the population. And that sounds like an impossible problem. So how do we use the information in this one sample to assess how much the means for other samples of 8 sandwiches might vary? So the idea here is we're going to use something called sampling with replacement. We can't repeatedly sample from the population of sandwiches with ants, but we can simulate the population. If we make lots of copies of the original sample and then take many random samples of the same size with replacement, we are coming as close as we can to repeatedly sampling from the real population. So this little picture shows everything, I think. So here you have, 6 little stick figures. And if we were sampling from those stick figures, you could just make lots of copies and sample from the stick figures. So basically the idea is we call it sampling with replacement. So after you take a sample, each case, or each data value, however you look at it, each data value is available to be selected again. Right, and that's what it says here. So that's what sampling with replacement is. And each sample selected in this way with replacement is called a bootstrap sample. So the idea is we can go through, we have our original sample, but we use the original sample, and then we sample with replacement from the original sample to create bootstrap samples. And bootstrap samples need to be the same size as the original sample to simulate a sampling distribution from section 3.1. And all values need to be present in the original sample. You can't introduce new values that were not present in the original sample. And because a bootstrap sample is selected with replacement, data values may be selected multiple times. In fact, they have to be selected multiple times, or every sample you selected would just be the original sample all over again, and then you wouldn't have any variability. For each bootstrap sample, we compute the statistic of interest, giving us a bootstrap statistic. If we take many bootstrap samples and compute a bootstrap statistic from each, the bootstrap distribution of these statistics will help us understand the distribution of the sample statistic. And then we use this bootstrap distribution to approximate the actual sampling distribution. So I know it's a ton of terminology right out of the gate here. That's just the way everything's going to be the rest of the semester. By the end of the semester, you're going to have about 130 vocabulary words. That's just the way this class is. So just make sure you're learning what this stuff means, right? If you see the word bootstrap, it means it's selected with replacement. And then everything else we do is generally the same. So let's go back and look a little bit more at bootstrap sampling and how it works. So here's our original sample of 8 sandwiches. And here's the number of ants that were on each sandwich. So that's our original data set. I'm just listing it here. And then below, we have 3 possible bootstrap samples from the original sample. So the rules are, let's go back 2 slides. The rules are they need to be the same size as the original sample. All values need to be present in the original sample. And data values can be selected multiple times. So those are the only 3 rules. All right, what about this first one? Is this a bootstrap sample? So just go through everything. Is it the same size? Well, here there's 8 numbers. Here there's 1, 2, 3, 4, 5, 6, 7. So even though all the other qualifications are satisfied, this is not a bootstrap sample because this is only size 7, and the original sample was size 8. All right, what about B here? So 22, 22, it's all 22s. Is that an allowable bootstrap sample? Well, just go through everything. Is it the same size? There are 8 values of 22 here, so it's same size. Do all of these numbers come from the original sample? Yeah, 22 is right there. So those are really the only 2 things we need to check if we're thinking that it is a bootstrap sample. So it turns out it is. Remember, values are allowed to be repeated. Nothing wrong with that. And what about this last one? Well, we can see it's the same size, size 8. So all we need to check is, are all these values in the original sample? 47 is there, 19 is there, 21 is there, 33 is not there. This value is an extra introduced value. It didn't come from the original sample, so it's not allowed. Therefore, this is not a bootstrap sample. And then the way this works is well, we're going to use technology to do this. But just imagine how this would work sort of in a classroom setting without technology. How would we do this? Well, it's really the same thing we've talked about all semester. We would put these numbers into a random number generator or put the numbers in a hat. and select them one at a time and just write them down. Whatever's randomly selected, we write down. You would pull one number out, write it down, put it back in the hat, mix it up, pull another number out, write it down. So sure, you could get 22 8 times in a row. Not likely, but it could happen. So as long as we're randomly selecting from these numbers and getting 8 new values that are combinations of these, then we've created Bootstrap samples. And once that happens, you create that Bootstrap distribution by taking the sample means. The Bootstrap statistic is a sample mean. In this case, it's a mean, but it could be a proportion. So if n is the size of the original sample, generate a Bootstrap samples of size n by sampling with replacement from the original. So that's what we just talked about, right? Put the numbers in a hat, mix them up, or use technology. And again, I will show you this exact problem at the end, how I generated all the stuff in StatKey. Then compute the Bootstrap statistic from each Bootstrap sample. So let's go back one slide. Here, the sample mean would be 22. The sample mean here was 34. And so every time you generate a new Bootstrap sample, you generate a new Bootstrap statistic, and then you collect these statistics and plot them on a dot plot. And that creates a Bootstrap distribution. And we use that Bootstrap distribution to simulate a sampling distribution. They are not the same thing, but we're using the Bootstrap distribution as a stand-in. It's like a stunt double or an approximation for the actual sampling distribution. So this diagram at the bottom explains everything really nicely, and it also points out something that gives students trouble, and I don't want anybody to miss this. Even though students do miss it every semester, I don't want anybody to miss it. So think about what we saw earlier. Our original sample was 8 ants on a sandwich, and then we took a sample statistic, x bar equals 34, or any other sample statistics, right? Standard deviation, that sort of thing. Then bootstrapping is a separate process. You take the original sample and you take these bootstrap samples from the original sample by sampling with replacement, using technology or numbers in a hat or whatever. And you can take as many of these as you want, usually at least 1,000 if you're using technology. Then from each bootstrap sample, you compute the bootstrap statistic, which in this case would be we call it a bootstrap mean or a sample mean. Then we have all these X bars from these bootstrap samples, and you collect those together and make a distribution out of that. That's exactly what we did in 3.1 when we made sampling distributions, except when we took our samples, they were all samples from the original population. Here we don't have access to the population, so we use this approximation procedure. So that's how this works. Just if you need to think about this a while or take notes on this, this is an important process to understand because we use it obviously for the rest of chapter 3. And this terminology we use the rest of the semester. So one thing I want to point out here is that the original sample statistic, whatever it is not related to this bootstrap distribution in any way. I mean, it could show up sort of coincidentally in the bootstrap distribution, but this bootstrap distribution does not depend on this original sample statistic at all. Keep that in mind as we progress through. So here's how we do it in StatKey. Again, I will show you this at the end. We'll come back and just redo this whole thing. But I did generate some graphs, so I put the instructions here in the notes so you can see how to do it. So if you do all this stuff, you will get this graph, or something like it. These are randomly generated, so we wouldn't expect them to look exactly the same. So if our sample is randomly selected, we treat this bootstrap distribution as an approximation of the actual sampling distribution of the sample statistic. So think about what's going on here, right? These are all sample means from bootstrap samples that were all taken with replacement from the original sample of 8 ants on sandwiches. Or 8 sandwiches with ants on them, I should say. Right, more than 8 ants on the sandwiches. And here's the variability. So the idea here is that we don't know what the sampling distribution looks like, but we think it looks sort of like this. The problem is this thing is going to be centered at the original sample statistic, even though it's not directly related to the sample statistic. It's going to be centered there because we're using our original sample mean as the population. And sampling distributions are centered at the population parameter. So if we're treating our original sample as just this little tiny population, then the sample statistic is a stand-in for the population parameter, so it's centered there. So I do want to point out the original sample statistic is 34. It is not this number, this mean. Please don't mess that up. That's the thing that people mess up. They use this as the center, and you're going to get some stuff wrong. If you do that, you have to center it at the original sample statistic. However, the variability given by the standard error, as we saw in 3.1, it shouldn't matter where this thing's centered. The amount of variability should be about the same, because the center depends on this one particular sample that you happen to take. But the variability shouldn't depend as much on sort of the quirks of this one sample compared to the population. So what we do is we center this thing at the original sample statistic, and then that is our variability. And then we can, if it's bell-shaped and symmetric, we use the 95% rule. Yeah, I already explained this, right? So each of the 1,000 dots in this bootstrap distribution is a bootstrap mean computed from a bootstrap sample of n equals 8 sandwiches. I just wanted to give you one slide with all the terminology sort of used together like this. Symmetric and bell-shaped, so that means 95% rule. And so what we do is we build a confidence interval because it's centered at the sample statistic, just like our confidence intervals were earlier. And so when we have a symmetric bell-shaped bootstrap distribution, we use this formula, sample statistic plus or minus 2 times the standard error. And SE is the standard error of the statistic estimated from the bootstrap distribution. And at the bottom, of course, does it look familiar? It should. It's the same formula we used in an earlier section in chapter 3. And so you might say, well, what's the difference? Why do we need this big, complicated procedure? Why can't we just use what we did in an earlier section? Well, in section 3.1, we were assuming that we had access to the population, and a population parameter, or had the means to take many, many samples from the population. In the real world, though, that's not feasible. If somebody has the means to do some sort of study, even if it's a silly study like counting ants on a sandwich, it's still prohibitively expensive, either with money or time or resources, to actually take thousands of samples. It would just take too long. So taking one good sample is just as good as taking lots and lots of samples. All right, so we're going to switch it up. We're going to move to a new example. And again, I can show you the stat key for this one at the end as well. So let me back up for one sec. If you want to stop here and pause it and like go back through everything about the ants on a sandwich example does come back next section. It's a great, easy to understand example. But in the interest of giving you a more even picture of what's going on, I'm going to keep running different examples at you, like I have done in the past. So don't look for shortcuts or anything like that. There are some similarities between the different types of problems, but there's really no shortcuts. Again, stat key at the end. All right, let's keep going. Let's talk about compassionate rats. So in a 2011 study, rats showed compassion that surprised scientists. 23 of the 30 rats in the study freed another trapped rat in their cage, even when chocolate served as a distraction, because rats love chocolate. Rats did not open the cage when it was empty or when there was a stuffed animal inside, only when a fellow rat was trapped. We wish to use this sample, so this 23 out of 30 rats in the study, to estimate the proportion of all rats that would show empathy in this way. So before we go farther, let's make sure we understand what's going on here. One thing I've noticed in the past, and I've taught this class over 20 times, is a lot of students want to just jump in and start solving the problem, because that's what you've been trained to do in math your whole life, is as soon as you read the problem, get cracking, get solving. We don't want to do that. We want to break everything all the way down, just like we've done earlier in chapter 3. If you find it unpleasant to break these problems down, I'm sorry, but that's what, probably a third of the test is going to be just on the problem breakdowns, as opposed to any sort of solving of a problem. You're going to have to solve stuff too, but you're still going to have to break it down. So make sure you can understand the sample statistic, the population parameter, and then anything about the variables, categorical or quantitative, explanatory or response. Here there's only one sample, so our response variable is either going to be categorical or quantitative. There's no explanatory variable. So the sample is the 30 rats, and then is the variable categorical or quantitative? If you're not sure, pause the video, think about it, work it out on your own. It'll help you in the future when these problems start coming rapid fire. Right now, we're still taking a lot of time and working through them. Right, it's categorical, because rats either help out their fellow rat or they don't. So there's only two categories, it's categorical. That means we have one sample, categorical, so our sample statistic is p hat, which would be our 23 divided by 30, and as a decimal, whatever that is. That means the population parameter is p, because you have to know the correspondences, and then we have to put a name, right? So p is the proportion of, well, it's going to be whatever the sample is, but in the population. So here, 23 of 30 rats freed another trapped rat. So we're interested in the proportion of all rats who would free one of their fellow rats, right? So this is the population proportion down here. Okay. So the relevant parameter, it's best estimate. I just talked about that. The parameter is p. The best estimate is p hat. And you want to give their values too. Describe how to use 30 small squares of paper to create one Bootstrap statistic. Use stat key or other technology to create a Bootstrap distribution. Describe the shape and center of the distribution. What is the value of the standard error? Now, everything's in the notes here. I'm going to show you the stat key at the end, because I don't want you working through the stat key right now. If you want to do that, go back through and just check your answers, because all the answers are in the PowerPoints. Use the standard error to find and interpret a 95% confidence interval for the proportion of rats likely to show empathy. And then a follow-up question at the end. Can we conclude that more than 75% of all rats show empathy? A lot going on here, so let's start breaking it down. We already did the first one, right? Right? P is the proportion of all rats that show empathy, right? So we already talked about that, and the best estimate is p hat, which is 23 out of 30. So for part B, let's talk about this. Let's describe how to use 30 small squares of paper to create one Bootstrap statistic. So I'm actually going to back up into the problem itself. So when we were talking about ants on a sandwich, that was a quantitative variable. So when you put the numbers in a hat, you mix them up and pull a number out to create your Bootstrap sample. This is a little bit different, because with a categorical variable, you don't write numbers down. You write yes or no, or like an X or a 0 or something like that. You would use symbols to simulate this. So what you would do is maybe you take all 30 pieces of paper, and each piece of paper simulates the behavior of one rat. 23 of the rats in the study did this thing, showed empathy. Maybe you put an X on the pieces of paper that represent the rats that did this thing. So 23 of the pieces of paper have an X. Put them all in a hat, mix them up. Now, when we create our Bootstrap samples, the samples have to be size 30, because we're going to be recording p hats for each Bootstrap sample. That means we have to pull 30 pieces of paper out. But the sampling is with replacement. So when we pull a piece of paper out, we look at it. It either has an X, meaning it's a rat that would free a trapped rat, or it doesn't, meaning it's one of the other rats. So you don't pull all 30 pieces of paper out, because if you did that, you'd have 23 out of 30 again, because that's how many have X's. You use with replacement. So you pull one out and you mark down, does it have an X or not? So just use, tally marks or something, or just put it on a calculator. And then you put that piece of paper back in, mix it up, pull out another piece. Does it have an X? If it does, mark it down. If it doesn't, that's fine, it doesn't. And you sample with replacement 30 times, and then you count the number of X's. The number of X's is your Bootstrap p hat. And then you start over, and you do 30 more, one at a time with replacement, count how many X's, that's another Bootstrap p hat. You take all those Bootstrap p hats, those Bootstrap statistics, you plot them on a graph, and that graph is a Bootstrap distribution. So that's what it says here, so I'll let you read it. It's what I just explained, but you definitely want to understand this. This could be on a test, and yes, you'd have to be able to come up with something similar on your own. So if you need more time, just pause it and read it. I'm going to keep moving. So here's the stat key for how to do this. I will go over this at the end. And here's what the distribution looks like. So I put 200 samples here. Let me point this out, something earlier. So notice that for step 4 here, I said a large number of samples is needed for the homework. I only did 200 just so that you could see the shape of the distribution real clearly. For illustrative purposes only, if I generate too many samples, sometimes the graph gets kind of weird looking. I just want you to be able to see the graph and have it look real nice. On the homework, it doesn't matter. On the homework, all you care about is the standard error. Okay, but I want to show you how these dots work, right? I want to show you what's going on. So we need to be able to see the details here. So the distribution is symmetric and bell-shaped. Sure, it's skewed a little bit to the left. It's fine. It's symmetric and bell-shaped enough. Centered at the original sample statistic p hat. Now here it just so happens to be the same number, right? 23 out of 30, 0.767, but that's not always true. This is just a coincidence in this case. Standard error, you want to keep the standard error to 3 decimal places for intermediate calculations, but that's how it works. So all we need this graph for is to read off the standard error. The standard error tells us how much variability there is among p hats if our original sample is indeed representative of the population of all rats. And so you just compute the confidence interval, right? So there's your formula. The original sample statistic, not the one from the graph, the one from the original sample. Plug everything else in, round it. On the homework, just follow the directions for rounding. Now we have to interpret the confidence interval. And this is something you have to work on, because on an exam, you absolutely will be required to interpret this. So what you have to do is you have to go back. We already answered this question, right? In part A, so this is the parameter. The parameter has a name, P, but it also has a description, right? It's the proportion of all rats that show this sort of empathy that's described in the problem. So we think, we're 95% confident that P is in that interval that we computed, right? So we're 95% confident that P is in this interval. But you can't just say that. You have to unpack the meaning of P and say the proportion of all rats that would show empathy is in this interval, right? So we're 95% confident the proportion of all rats that show empathy is between these two numbers. So your last step, even if you don't have to do it on the homework, and when you have to do it on the homework, a lot of times it's multiple choice. Students have a tendency to guess a lot when it's multiple choice, but on a test, this will absolutely be something that you'd have to write out, and yes, it'll be worth a lot of points. You're going to have to practice unpacking the meaning of the parameter back in context of the confidence interval. All right. Okay, last question. Can we conclude more than 75% of rats show empathy? Well, here's the thing. Our original sample statistic is bigger than 75%. So you might think, well, sure, if the original sample is more than 75%, then yeah, sure. Probably more than 75% of rats would do this thing. But we know that samples vary. And if you're going to conclusively claim that something is true to some level of confidence, it has to be not contained within this interval, because there's numbers in this interval less than 75%. So that means it's plausible that it could be less than 75%. So we can't conclude that P is greater than 75%. Again, if you need more time on this, pause it here, and then go back and look at 3.1 and 3.2, all the non-stat key stuff. And you'll see that we use confidence intervals not just to find a range of values, but also to evaluate claims about values that are conjectured or suggested. Right? We can use a confidence interval to make evaluations, not just estimate. All right, that's the end of the section. I'm going to show you the stat key now. So let me put this in. We put this in reading view. All right. And I'll open up my stat key. All right. I'll put stat key over here. That's fine. All right. So let me get back where we were. All right, here we go. So I'm going back to the original Bootstrap sample example right here. Making a Bootstrap, this is where I'm at. Making a Bootstrap distribution. There we go. You guys should be able to read that fine. So this is slide 109, for those of you keeping track, if you have the slides open separately. So we're going to go to stat key, select Bootstrap confidence intervals here. So we're doing the ants on a sandwich. So we're going to do confidence interval for a mean, median, standard deviation. So click on that. Then we're going to go to edit data here. And we're just going to clear all this out. And then we're just going to type in ants, because we're claiming that there's a header row. So you need to name it something. Oh, sorry, in the instructions I said don't do that. Let's deselect that. Just clear it completely out. Then edit the data and enter the sandwich ants data set. So here's our sandwich ants data set, right, 43. So just enter it as a single column. You don't have to enter anything by hand like this on the homework, but you might use this program in the future to do other types of studies. So I entered everything in, just do it as a single column. Right, 43, 59, 22, 25, 36, 47, 19, 21. All right. And then we're going to generate 1,000 samples. The center and spread of the distribution are given by the original sample statistic X bar. So it's not this, right? The original sample statistic is over here. Right here, 34. That's our center. It's over here on this side. But the standard error is here. We do use the standard error from the distribution. You just have to remember it. And you can see that it looks similar to the graph in my PowerPoints, but again, it's randomly generated, so it's a little bit different, right? So here, 4.893, 4.892. Notice that standard error is pretty close. Every time you do this, your standard error value is going to be really close, but your mean might not be. Here, the mean is 34.3. Here it's 33.8. So the mean isn't that close, but the standard error is. It has to do with how the variability works. Even if your samples are a little bit off, the variability remains generally unchanged. So that's why we use this technique. All right, now let me show you how to do the rats with compassion in StatKey. So we're going to do the same thing here. Bootstrap confidence interval, it's a CI for a single proportion. Now we're going to enter the custom data. We're going to click Edit Data. And for count, we're going to put in 23. out of 30. And again, at least 1,000 samples. So notice that this doesn't look like what I did here, but because I did 1,000 samples, so it's kind of blurry, right? If you generate samples like more slowly, you can see the graph kind of build up. But as soon as you get, there's 400, 500, 6, once you get to about 600, everything looks real blurry. Same sort of thing, there's our standard error, right, 0.08, or so it's off by 1/1000th. The mean here is 0.767, 0.766, so pretty accurate. And all you're using these graphs for is this standard error, so that you can go sample statistic plus or minus standard error. You're going to get a confidence interval, sample statistic plus or minus 2 times the standard error. You're going to get a confidence interval. You interpret the confidence interval. And then from there, once you have a confidence interval, the stuff in this section is the same as section 3.2. All right, well, that's it for this video. So try both of those, make sure you can do it. There are others, I do want to point out, there are difference of means, difference of proportion, slope, and correlation. More of those examples coming in the next slides. For this homework, for what you need, it's really just proportion and mean. It's just one of these two. All right, that's it. And let me know if you have any questions, and I'll see you next video. Bye-bye now.